Okay guys, next we discuss electric potential due to point charge. Suppose we have a point charge plus Q, and this point charge I suppose it to be at point O. Now this point charge has field around it, and we suppose 2 points in the field of this point charge. Suppose we have point A and we have point B, and we are going, and this is positive point charge, so the direction of the electric field of this point charge is away from the charge. Now suppose we are moving a test charge. Let the test charge is also Q naught, but it's also a positive charge from point A to point B in this way. Now the distance from this source charge, a point charge, to this point B is RB, and the distance from this point charge to point A is RA respectively. Now the electric potential difference in bringing the potential difference in bringing a test charge Q naught, this test charge Q naught, a test charge which is Q naught in the field of point charge plus Q from point A to B is given by, we already calculated a formula for that. The potential difference in bringing a charge from point A to B is VB minus VA, which is equal to minus integral of E dot dr, and the limit of the integrals are from point A to B, because we are bringing this test charge Q naught from point A to point B. So here we have the potential VA, and here we have the potential VB. Here the potential is VA, and here the potential is VB. Now the difference in potential, the potential difference in bringing a test charge Q naught from this point A to point B is given by this relation. Now we can also write it as VB minus VA is equal to minus integral of E dot dr, but point A at a distance RA from the test charge, and point B is at a distance RB from the test charge. Let's say this is equation number 1. Now we know that the electric field, by field I mean the electric field of a point charge at a distance R is given by, if we have, let's suppose, a point charge Q, its electric field at this point P, which is at a distance R, is given by E is equal to 1 over 4 pi epsilon naught Q over R square. If I use the direction of this electric field, then we have the unit vector R cap here. Now using this is equation number 2. Using equation 2 and 1, we have VB minus VA is equal to, now if I put this value here, then this 1 over Q into 1 over 4 pi epsilon naught, they are constant, so I will bring it outside of the integral. So here we have minus Q over 4 pi epsilon naught, and we left with integral of RA to RB, and we have R cap over R square. It's from this, and we have this d r unit vector. Now this dr unit vector can also be written like this. So here I will use the extra work. Dr unit vector is basically its magnitude times its direction. So this term will give us this term, r cap dot dr cap dr, like r cap dot dr unit vector will give us r cap dot dr into r cap. Now this will become dr times r cap dot r cap. From this we got 1 because these are the unit vector. So this whole quantity r cap dot dr is equal to dr. So we can write here this change in potential, a potential difference VB minus VA, which is equal to minus Q over 4 pi epsilon naught, and we have integral from RA to RB, and we have dr over r square. Now if we solve this integral, if I solve this integral, then I get VB minus VA, which is equal to minus Q over 4 pi epsilon naught, and from this I will get minus 1 over r. No, it's 1 over r, sorry, 1 over r, and the limits are from RA to RB. If I put the limits here, this is minus, yes, minus 1 over r. Now this minus minus will become plus. So if I put the limit, the final expression will be Q over 4 pi epsilon naught into 1 over RB minus 1 over RA. This is the potential difference VB minus VA. Now equation 3, I call it equation, let's suppose 3. This equation 3 gives the potential difference between point A and B. Point A and B. Now here we simplify the integral by choosing to move the test charge from point A to point B along the radial direction. We solve the integral by moving the point charge from point A to B along the radial direction or along the radial path. But we know that the potential is independent of the path. So equation 3, this equation 3 holds for any path between these 2 points A and B. So if the path is curved, then we have the same results given by equation number 3. Okay, next we have absolute electric potential. Electric potential. Now the work done in bringing a unit positive charge from infinity to any known point against electric field is known as absolute potential. Like suppose we have a positive charge, and around this positive charge we have the field lines. These represent the field lines. Now the work done in moving a test charge from, let's say, infinity to some known point against this electric field, because the direction of electric field is this one, in we are moving the charge against this electric field, then it is called absolute potential. Now we know that the potential difference between 2 points A and B is given by equation number 3, which is VB minus VA, which is equal to Q over 4 pi epsilon naught, and we have 1 over RB minus 1 over RA. Now for absolute potential over point A will be at infinity. So the distance from this point charge to this point is RA, which is infinity. Now for absolute potential, I will write it here. Now for absolute potential, because for absolute potential we are moving the point charge from infinity to a known point. So for absolute potential, we suppose the point A at infinity. So under this condition we can write RA is equal to infinity, and we know that at infinity the potential will be 0. So VA is equal to 0 at infinity. Now using this value, RA is equal to infinity and VA is equal to 0, here in this equation we get, I will write it here, we get VB minus VA is infinity, which is equal to Q over 4 pi, VA is 0, sorry, it's not infinity, like the value of potential at infinity is 0. So VA, which is at infinity, is equal to 0, which is equal to Q over 4 pi epsilon naught times 1 over RB minus 1 over RA. So for RA I will put infinity. So this will become equal to VB, which is equal to Q over 4 pi epsilon naught times 1 over RB minus 0, because 1 over infinity is equal to 0. So this VB is equal to Q over 4 pi epsilon naught 1 over RB. Now this equation represents the absolute potential. In general, we can write the absolute potential as V, which is equal to 1 over 4 pi epsilon naught Q over R. This is the absolute value of potential, like moving up test charge from infinity to some known point against the electric field of some point charge. these are the electric field, this point charge. So we are moving this test charge Q naught from RA is equal to infinity to RB. So we have this value, this is called absolute potential.